Welcome to the video for Local and Global Extrema Day 2. Okay, in this video we're going to focus on finding global extrema by using closed intervals and critical values. Again, the local ones we'll hold off on until day 3. So right now we're looking for just global, or another word for that is absolute. And we're going to use the extreme value theorem, which says that if a function is continuous on a closed interval, then the function has both an absolute maximum and an absolute minimum value on the interval. Let's go ahead and write that word in there, absolute. So what we need to do is take a look at our function and check for a couple things. Check to see that it's continuous, and then check to see that it's continuous over the entire closed interval. And then if it is, we will have both an absolute maximum and an absolute minimum. So this is the extreme value theorem, and let's practice applying it. So example 3 here asks us to determine if the extreme value theorem applies. And I'm first going to state whether it does or does not, and then we're going to see if we can find any absolute extrema regardless of whether the EVT applies. So in part A, f is not continuous. You can see that the function is not continuous. So EVT does not apply. And more specifically, we need to say that it is not continuous on the interval 0 to 2. We could alternatively say that f is discontinuous at 1 and 1 is in the interval 0 to 2. I'm going to zoom in so that I can write more clearly. So the EVT does not apply, but that does not mean there is no absolute max or absolute min. It just means they're not guaranteed. And when we look at the graph, we can see that there is an absolute min. So we can write that down, absolute min of 0 at x equals 2. However, when it comes to finding the absolute max, the highest point is not actually a point. It's not included there. So we cannot identify that as an absolute max. So we write that there is no absolute max. Going on to the second graph, we see that it has a discontinuity at 1 and at 2, so it's no longer continuous on the closed interval. So we could write that as f does not include the endpoints of the interval 0 to 2. Or we could say f is not continuous on the entire interval 0 to 2. So the EVT does not apply. EVT does not apply. So we still want to check, though, to see if there's an absolute max or an absolute min. So starting with the max, the highest point is infinity. However, we can't identify the point because infinity is more of an idea, so there is no absolute max. And then we go to the lowest point, and the lowest point appears to be located there, but again, this is an open circle, so we have no absolute min. So I'm going to leave part C for you to try, and then we'll come back together on part D. So go ahead and pause the video here and take a shot at doing part C. Alright, the function is not continuous at x equals 1, so the EVT does not apply, but we still have an absolute max because this point is included, so a max of 3 at x equals 2, and a min of approximately 1/2 at x equals 0. So finally we'll go to part D, and part D, the EVT does not apply, so the reason for that is the endpoints are not included because it is not continuous on the entire interval. 0 to 2. But we might still be able to find an absolute max, and we do. We have a absolute max of 3, and that occurs at x equals, oh, I don't know, about 1/2. And then we also have a absolute min, and the absolute min of, I don't know, about 1/3, 1/4 at x equals 3/2. Okay, so the takeaway from this, the EVT guarantees both. So if the extreme value theorem passes, we get both a max and a minimum. But if it fails, then it's still possible to find some of them some of the time. Okay, so when the EVT fails, we still need to be able to find ways to do this analytically if we're given an equation rather than a graph. And we're going to get to that, but for now let's learn some vocab words that we're going to use pretty often. A critical value of a function is a value x equals c that is in the domain of f. So it has to actually be in the domain such that f prime of c equals 0 or f prime of c does not exist. And there's our calculus right there. Critical values are going to occur where the derivative is 0 or where the derivative does not exist. And the x-coordinate is considered the critical value, and then if we plug that value into the function, that's the critical point. And what we find is that a absolute maximum or absolute minimum can only occur at a critical value or at the endpoint of the interval. And as we progress through this section, we'll see why that is true. Okay, looks like we're going to also actually hit some local extrema. Thought that was the next day, but today, relative local max or the relative or local min. So just like we have global and absolute, we also have relative and local, and they're used interchangeably. So a local maximum occurs when there is no y values greater than f of c on an interval. So basically, if we come up to a high point and immediately to the left and immediately to the right we are below that high point, we're at a local maximum. And that can occur any of variety of ways. The way I've drawn, maybe we get something kind of like that. That's a local maximum. Or even we can have a local max at a discontinuity. We can have a local max where we have a discontinuity and then a point above, and then even we can have local maximums occur in flat constant areas like this because there are no y values greater than that point. So even though they're equal, there's no y values greater. And then we can flip all those upside down and get the same for the relative or local minimum. So local minimum can occur at a low point, and those can take on all the same shapes except upside down. So what we have here is the idea of how we find the local or relative maxes and mins. They occur only at critical values. So this is where the calculus comes in. We're going to need to find the critical values. And another subtlety is they occur on an open interval. So that means we don't want to include endpoints because they're at the end of a closed interval. So that's a real minor subtlety, and we'll kind of pick it up as we see these. It should be noted that just because a critical value exists It doesn't mean that there is going to be an extrema there. It just means that there is the potential for the extrema to occur there. The example given here is x to the third. If we find the critical value of that, we see that f prime of x is 3x squared, and there is a critical value at x equals 0, but we know that in that curve, x to the third, there is no extrema at x equals 0. So let's take a look at a curve that we've looked at earlier and identify all the critical values. So first off, we have an endpoint at A, and at this point f prime of A does not exist. So we have a critical value at A. And we could say the same thing as the endpoint f, because f prime of f does not exist. We have a critical value at x equals f. Now those are endpoints on the interval, so we can't include those as local max or local mins. So let's just kind of set those off to the side, but let's take a look at the other ones. We're going to have a critical value at b, critical value at x equals b. We're going to have, because f prime of b is 0, we can see that the slope at that point is 0. We're going to have a critical value at c, because f prime of c does not exist. We're going to have a critical value at d, because there's another 0 slope, x equals d, because f prime of c is 0. And then we'll also have a critical value at x equals e, and that's because f prime of c is 0 there. We can see 0 slope. And now that we've identified all of our critical values, we need to identify whether we have a local maximum or a local minimum there. So at b, looks like we are coming to a high point, so this is a local max. At c, we're coming to a low point, so that is a local min. At d, we come to a high point, so that is a local max. And finally, at e, we come to a low point, so that is a local min. And incidentally, though it doesn't ask for it, x equals d is the global max. So we could also, if we wanted to say that there's a global max at x equals d. All right, I'm going to leave example 5 to you to take a shot at it. So go ahead and pause the video here. I will write in the solutions and you do the same, and then check what you have against mine. Pause now. Alright, so at -3, the function's derivative is undefined, and we get a local max. At 1, the function's derivative is undefined, and we actually have neither a max or a min because we're less than on the left side and greater than on the right side. At 1, we have a local min. Again, this is a discontinuous spot, so we have a local min. And at 2, we have a local min. We're at a point lower than everything to the left and right of that point. And then finally at, that is all of them. The endpoints, the derivative is undefined because it's just one-sided, but we can't talk about local extrema for those. So there you have it. There's all our local mins and local maxes. If we went about finding our global extrema, we have a global max of a global min of -2, and that occurs at x equals -4, and we have a global max of 2, and that occurs at all x from -1 to 1. All right, let's do this analytically because that's where we're heading. We want to be able to do this from an equation. So first off, we need to find the domain of the function, and part A is a polynomial, so the domain of f is all real numbers, so that's useful to us. And then we want to find critical values, and remember we find critical values by setting the derivative equal to 0. So first we're going to take the derivative of the function, and here we have the derivative, pretty straightforward power rule all the way across. And then we want to set that derivative equal to 0. We want to find where is the derivative 0 or does not exist. So when we set this derivative equal to 0, we can factor out an x, and then it looks like we can factor it even further, and we get 2x plus 1 times x minus 2 equals 0, giving us critical values at x equals 0, at x equals -1/2, and x equals 2. So there's our three critical values. Those are where possible maxes or mins can occur. It's not guaranteed. We're going to learn in the next couple days how to determine whether a max or a min occurs there. So if we were to think about this analytically, we have a fourth degree function which probably looks something like that, and we can see that there's the potential for 3 maxes or mins, and we have 3 critical values. So that kind of fits with our understanding of polynomials. All right, let's look at 6b. 6b is a continuous function, so again our domain for g is all real numbers, and finding derivatives of absolute value functions is never easy, so it might be easier to think of this as a graph. So what we have here is we have an absolute value function that is shifted to the right 4 units. It's been reflected and shifted up 2 units. So graphically we've got 1, 2, 3, 4 units to the right, up 2 units, and then it's reflected downward. So when we look at this graphically, we see that the derivative can exist everywhere except at x equals 4. So f prime of x does not exist at x equals 4. So there we have it. Our critical value is at x equals 4. So, and we can see off of our graph that that is both a global maximum and a local maximum. So finally, the last one. This is going to take some fancy pants algebra, but what we have here is there are no even roots, there is no denominator, there's no log, so our domain is not restricted at all. Our domain is all real numbers. And if we go about taking the derivative of f, what we want to do is use the product rule. So the derivative of the first times the second plus the first times the derivative of the second. And that's f prime of x. If we go about cleaning this up, we can combine like terms. I'm going to do all this off time, and you can compare. So go and pause if you want to try to clean it up yourself. Okay, so we distributed the negative, and then we distributed the 3/5 in, and then we combined our like terms. And then this last step is kind of the tricky one. We factored out the least power, and from there we are able to use the zero product property. And we find that we're going to have a critical value at x equals 0, because the function is undefined, or the derivative is undefined. F prime does not exist, because that causes a 0 in the denominator. And we also have a critical value at x equals 12/8, or very simply 3/2. And that's because f prime of 3/2 is equal to 0. If we compare those to our graphs, then the graph of this, looking at it on a calculator, we get something that looks something like that. And at 0, we have a vertical tangent line, and that's going to oftentimes occur when the derivative does not exist. And then at 3/2, we have a horizontal tangent line, and that's where our derivative is equal to 0. So a tip is anytime you have a fractional exponent, you should be in cusp alert. You have the potential for a cusp, or you have the potential for a vertical tangent line. So when we get to sketching graphs, this fractional exponent is something you should clue in as to its meaning. Okay, thank you for watching the video. The big pickup that you should be getting from this video is that a critical value occurs when f prime of x is equal to 0 or f prime of x does not exist. A subtlety is that the critical value has to be in the domain of f. It's a subtle detail, but we're going to be finding critical values a lot over the coming days. So thanks for watching, and until next time, have a good day.